Today we're going to look at basic gyrator circuits. And the reason that we want to use a gyrator is that the inductors that we looked at when we fabricate them in CMOS are quite big and lossy. So what we're going to do is replace large lossy inductors with circuits that mimic inductors. So if we look at our basic gyrator circuit, what we're going to do is use a couple of transconductors connected in negative feedback. So for instance, we might have a differential transconductor where we connect the circuit as follows. This transconductor has a transconductance of big GM1. It's a differential to single-ended transconductor. We have a feedback transconductor. That has a value of GM2. And we feed the output signal of that feedback transconductor back to the input of the first transconductor. At the node between the two transconductors, we place a capacitor that has a value of C. So if we were to put a test voltage source with a value of Vx and measure the current Ix that flows from it into this circuit, we could find the following. So we'll label the output, or the label connected to the capacitor, node Y. So the first thing that we could say is that Vy is equal to GM1 times Vx times the impedance at this node, and assuming that these are ideal transconductors, the only impedance at the node is due to the capacitor, C. So this would be times 1 over SC, the impedance of the capacitor. Now if we measure the current coming from the GM2 device, and we will call this current IO, we could say that IO is equal to minus GM2 times Vy. Note the minus sign is because the input is on the inverting terminal of this transconductor. We can also say that IO is equal to minus IX. If this is an ideal transconductor, no current flows into the transconductor, so all of the current flowing from IO has to equal the opposite of the current flowing from IX. Alright, making a few substitutions, we can say that IX is equal to big GM1 times GM2 divided by SC times Vx, and manipulating this a little bit more, we can say that Vx over Ix is equal to the input impedance, Zn, which is equal to S times C divided by GM1 GM2. Now we know that the impedance of an inductor, ZL, is equal to S times L. And so what we can see here is that this looks like an inductive impedance. It's directly proportional to the frequency, so the impedance increases as frequency increases. And in this case, our L looks like the C divided by GM1 over GM2. Or sorry, divided by GM1 times GM2. So here we can say L is equal to, or L equivalent is equal to C divided by GM1 times GM2. So our gyrator circuit looks like an inductor that has this value, C divided by GM1 times GM2. Alright, let's quickly look at how we might make one of these GM devices based on circuits that we've looked at so far during the course. There are several ways we might make a GM. So one way we might make a GM is to use a current source to bias a MOS device, where we put an input voltage into the device and take an output current from the drain of the device. In this case, the big GM would be equal to minus the little GM of the device itself. We could also bias a MOS device with a current source, connect the gate of the device to a DC voltage we'll call VB, and put our input in on the source of the device. This would be a common gate configuration. And again, we would take an output current from the drain of the device. Here, our big GM would be equal to little GM of the device. And you might imagine that we could also figure out a way to use the common drain configuration to provide us, common drain configuration to provide us a little GM. In this case, we put our input into the gate of the device, bias the device with a current source at the source of the device, and take our output current, I out, from the source of the device. And in this case, our big GM is also equal to little GM. Now, the circuits that we looked at on the prior slide were differential transconductors. So you can imagine one way to make a differential transconductor with a single-ended output would be our differential pair that we've looked at quite frequently with a current mirror load. So here's our differential pair with a current mirror load. We have a current source to bias the devices. We connect one side of this differential pair to a DC bias VB and the other side of the differential pair to our input voltage VI, and we take the output current flowing through the device. We could also use current source loads in a very similar configuration. We connect one side of the differential pair to a DC voltage VB, put our input voltage in on the other side, and take a current I out from the opposite side of the device. In either of these cases, our big GM would simply be equal to little GM of the differential pair device. Alright, so we'll continue our investigation of gyrator circuits on the next slide.